coming?
It's coming, okay.
Okay. Okay. Actually, I don't think I've heard from anybody on the homework except you guys. So,
Struggle.
okay. Well, it's tradition in this class,
Struggle?
particularly for this assignment, yes.
Oh, good.
Or are you talking about second one?
Yes.
So,
Okay. Okay.
That's true.
Certainly more so than the first one.
can we, okay, the one that I was asking you about earlier?
Yeah.
number 5.
Yeah.
Okay, so, the reason that I was asking you the question about, like, LU and pivoting
Yeah.
is because most of the chapters about LU, but you
Yeah.
said they're one and the same, sort of?
Yeah, different viewpoints on the same thing. Because, years ago you learned about Gaussian elimination, you also learned about row interchanges, but what wasn't really discussed back then was you end up with an LU decomposition from that, and now you see what you do.
So in LU, the lower is always unit?
Yes. Because
Okay.
you always have one diagonals, and then you have your multipliers below that. But this problem 5, this problem is not about the nuts and bolts of LU.
Okay.
It's how you would use LU if you had it for solving a larger problem. And the idea is, particularly for parts A and B, there's a dumb way and a smart way to carry out the computation, and the idea is to avoid the dumb way. So that's one way to look at it.
This is the algorithm,
No way
right?
we could get you to tell us what the dumb way is, right?
Wait, what?
The dumb way was the algorithm that you gave us in the notes.
You mean just the Gaussian elimination of partial pivoting? Or,
Yeah.
Yeah, that.
Well, no, that's not the dumb way because, all three of these parts involve some sort of solving a system, and for that purpose, all the things we've seen, LU, pivoting, substitution, etc., are tools. And this problem is about how do you use those tools wisely
Okay.
to compute these things.
So the general algorithm that you gave us in class, the one that you said don't just write this one down.
Right.
Okay, would it be right to say we're taking that and modifying it to our specific problem? Are we modifying that algorithm or writing a new one?
You're writing a new one in which LU, etc., plays a role. Yeah. And so the question is, well, what are you applying it to?
Well, we're using, okay, so kind of we're using all the parts, so we're using Gaussian elimination, LU, pivoting, to certain parts to
Yeah. And
the smartest, whatever, like you said, the smart way.
Yeah, and you're doing those things and other things
Right.
to do what's
But
right.
Algorithm.
Gaussian elimination is not separate from LU and pivoting. Right?
No,
Because they use Gaussian
Yeah,
elimination.
you might as well think of them as one and the same thing.
Right.
Yeah.
Okay. And when you say, like, I know the first thing you want us to do is describe the algorithm. So like we're literally just like writing about what it's doing. Like
Yeah, and it's something where, I mean, if you wanted, you could write code, but or if not code, like the pseudocode like formats so that if you were to try to implement this in MATLAB, then you could from its description.
So maybe like the pseudocode with explanation.
Yeah.
Like with, comments and explanation.
Yeah. And so one important thing to keep in mind is, for all the different things you could do, how much do they cost? I mean, we went over the cost of LU and forward and back substitution, but there's other operations, like for instance, Well, I'll just write them down. What?
Because
Nothing.
you said, I'm gonna write this down. She pointed at me like, pick up your pen and write
She
it
was
down.
ordering
I said,
her.
"Will you write it down yourself?"
Well, she's looking out for you.
I was looking out for
Thanks,
you.
Sam. You're the best.
Man, I should have eyes in the back of my head.
You miss all the fun stuff.
Well, not all of it, evidently. Okay. So cost of, okay, actually I didn't say other operations. There's certain ones we've already talked about, so I don't need to repeat that. Other operations. Okay, one is a dot product of, so like A transpose B of two vectors. Well, that takes, well, really 2n minus 1 floating point operations. This chalk is awful. Okay. Because you're carrying out n multiplications, you're multiplying corresponding elements, and you're adding them all up, so that's n minus 1 addition. So that's cheap, so that's good. And another one, matrix vector product. And we're going to assume everything is like, n by n matrix or an n vector. So y is equal to ax. Well, you're computing n elements of y, and each of those elements is a dot product. So you can just multiply the above by n. Alright, so it's order of magnitude more expensive, but not horrible. I mean, forward and back substitution are order n squared operations too. And finally, the worst of them all, matrix product. So C is equal to AB. Oh, what's up with this dang chalk? Okay. And I could tailor this for a case where A and B are different sizes, but we'll stick with everything be n by n. Well, you're computing n squared elements, and each of those involves a dot product. You're taking a dot product of a row A with a column B. So I can take this and multiply by n squared. So 2n cubed minus n squared floating point operation. So you don't want to do that unless you absolutely have to. And of course, you have Gaussian elimination. I've mentioned that a few times before. It's 2/3 n cubed. There's computing an inverse explicitly, so that's 8/3 n cubed. And then the two substitutions are n squared. So that's something to keep in mind. I'm pointing this out because this is how you determine the dumb way. Dumb is in terms of excessive flops compared to what you could otherwise do.
And the K is just a power on the matrix A.
Yes. So K can be anything. And in part C, there's a M. Probably best to assume that these values could be large.
Right.
Okay.
So, when you do powers of matrices, it works the same, right? Like, as powers of like an X, in the sense that you raise the power to a power you multiply, so you could switch the -1 and the K when you're finding the inverse. You can find the inverse of just A.
Oh,
You get what I'm saying? Do you understand
okay,
what
so
I'm
you're
saying?
saying like A to the K inverse
Inverse.
is the same as A inverse.
Right, that's
Yeah,
what
you
I'm
can do that.
Okay.
Okay. You might want to said about computing inverses.
You're right.
Okay, and there's something else. Oh, yeah, and as long as we're talking about powers of matrix, so each of these would be a matrix product.
Right.
Yeah.
But you're not like
Which we don't
explaining.
want. Right.
Definitely don't want. Yeah. Or just if you could find a better way to do it. Yeah. the so in general, like just to summarize, so like just solving a system, Ax equals B. So using the most efficient way we know of for a general case, so that would be 2/3 n cubed. And there's a couple of more terms that are n squared that are less significant, but that's something to keep in mind for comparing to whatever else you might do.
So number 4 is good, right?
Or is that the?
I mean the floss. I mean.
Yes. Again, assuming you don't have something better. So, because I mean, anything in cubed is not great, but sometimes you can't avoid it. And in the case of this particular problem, you can come up with multiple options that are all order n cubed operations, but the coefficient in front of the n cubed matters. So as coefficients go, that's pretty good. So in other words, you definitely would rather have that than
2.
that,
So things less than 1.
or just smaller than the alternatives.
Good.
But like for example, when I did a comparison last time of solving Ax equals B this way, like Gaussian elimination, LU forward back substitution, versus computing A inverse and then performing X is equal to A inverse B. So one's 2/3 n cubed and the other is 8/3 n cubed. So it's clear cut then too, even though the order of magnitude of the operations is the same.
Okay, last question.
Yeah.
Have we done, you had told us a few weeks ago that we hadn't done enough in class yet to do number 1. Have we done enough? I mean, you've mentioned.
That's coming today.
Okay.
Well,
we'll
yeah, just because it's about positive definite matrices, and I haven't really covered that yet.
Right, okay.
Okay. All right. So, which problems have you worked on?
I've finished 2 and 4.
Oh, okay,
I'm working on
right.
number 3. I mean
Okay.
number 5.
Right.
And I haven't touched 1 and 3 yet.
Okay. Yeah. Well, those will be fun.
What?
Those will be fun.
Oh. You're fun and our fun.
It's very fun.
Way on the opposite side.
I know. Okay. All right. So, well, now let's get to the point where you can touch all of those problems. Okay. Because I mentioned a little while ago that, okay, for solving a system, is 2/3 n cubed is the best you could do in a general case. But in this chapter that hopefully I'll cover today, but if not, no biggie, it's a short chapter though. There are certain special classes of matrices for which you can do better. It's important to take any properties that they have into account to solve Ax equals B or perform other tasks more efficiently. So, okay. So I have 2 classes of matrices in particular that I'll talk about. So first, this is one of my favorites because of all the nice properties it has. Positive definites systems. Or in other words, Ax equals B systems that have positive definite matrices. Okay. So, matrix A is symmetric positive definite. Yeah, so first it has to be symmetric, so A transpose equals A. And this strange property that this quantity, X transpose AX, which is a number because AX is a vector, and then X transpose times that, that's a dot product. So it's a dot product of X with AX. must be strictly positive for any non-zero vector x. I mean, if x is 0, but it's going to be 0, there's no getting around that. But otherwise, it needs to be strictly positive. Oh boy. Okay. Now, there's some nice consequences of this definition, and you could take some of these as equivalent definitions of positive definiteness. So it should keep in mind the term positive definite, sometimes that's used by itself, but it only applies to symmetric matrices. I mean, it's possible to have this happen if matrix is not symmetric, but we don't call it positive definite. Actually, I'm not sure what we do call in that case. Okay, so first of all, all of the eigenvalues of a positive definite matrix are strictly positive. And the way you can see this from the definition is that if x happens to be an eigenvector of A, then AX would be lambda x, and you get lambda norm of x squared must be positive. The only way that could happen is if lambda itself is positive. All right, so positive eigenvalues. In fact, I often use this as my alternative definition of positive definite matrix because this is an if and only a thing. Okay. One consequence of that is the determinant has to be positive because the determinant is a product of all the eigenvalues. So, in other words, any symmetric positive definite matrix is non-singular or invertible. Also, the diagonal entries are all strictly positive. So in fact, that would be one easy way to rule out a matrix being positive definite if any of the diagonal entries are non-positive. And that's not an if and only a thing, but it's something you can check. And the way you can see that is if you let x be equal to EI, the ith column of identity, then x transpose AX would be AII, and that has to be positive. Okay. Also, whatever is the largest entry of A in absolute value has to be on a diagonal. So it's not necessary or sufficient, for that matter, to have in order to have a symmetric positive definite matrix, it is neither necessary nor sufficient for all the individual entries to be positive. In fact, yes, so you could have a matrix that every entry is positive, but it fails to be positive definite. So for instance, if the off-diagonal entries tend to be the larger ones, that's when it would not be positive definite. Okay. And symmetric positive definite matrices come up in certain important applications, for instance, involving certain kinds of differential equations. Well, those of you who've taken any PDE classes, like for instance in 606, we saw certain operators, like Sturm-Liouville operators that were positive definite, they have positive eigenvalues. So that actually corresponds very closely to this. So here we're talking about positive definite matrices, but you can have positive definite linear operators, and it's often determined where you're working with a more general inner product, and you have the same positivity requirement for the eigenvalues. Okay. But the trouble is, it is, in general, not easy to tell if a matrix, like just by looking at it, is positive definite.
Excuse me, so in which of these, the off diagonal one is there one of those properties or somewhere?
Okay.
We have to have off diagonals to be the same, to be symmetric, right?
Well, yeah, like A12 equals A21. Yeah, you have to have that.
So this one is where, I mean, is hiding in which of these four properties or I don't know.
Oh, well, what about that?
Okay.
Yeah, so it's not hiding.
Okay.
Okay. All right.
Do all four of the properties have to be true, or just one of the four?
Oh, well, okay, these are, if it's positive definite, all four of these are true.
And what if we're trying to prove that it's positive?
You could prove all four.
No, I think the
So all
question
four-
said that it is already positive definite.
These are each necessary but not sufficient, right? Conditions.
Yes.
Positive definiteness applies to them, but they don't imply positive.
Right, right.
Okay.
Yeah.
Gotcha.
Okay.
Unless you have all four of them.
Well, in fact, there are other properties besides this that I can name. But, okay. So, yeah, like Tavis was saying, positive definite means you have all of these, but I can come up with a matrix that satisfies all these conditions and it can still fail to be positive definite.
Okay.
Although I'd have a hard time doing it.
Not my favorite answer, but.
Okay.
Well,
Okay.
I mean, like, if you're trying to show that something was positive definite, there has to be a way.
Oh, that's what I'm covering next.
Okay, cool.
All right, so that would be your favorite answer? So-
Yeah.
Okay. Yeah, because that's what's good. Yeah, that was my segue into that is, yeah, it's not easy, but here's how you do it.
Perfect. Okay.
Okay. And unfortunately, it's not a very efficient process either. Oh, you know what? You've seen this before, but it was a long time ago, like almost 5 years ago.
And I'm just remember that.
Well, no, you're not. But I just remember covering that back then.
But some class or something?
Yeah. So now I can recall terminology that I brought up much more recently in this class for when establishing the existence of the LU decomposition. So if we recall, the leading principal submatrices of A, I'll define them as AK, if I did that then, is just like the upper left K by K block. So if this is your entire matrix A, whoops. So if you have your entire matrix, then A1 would just be your A11 entry, and then you have A2 is your 2 by 2 block, and so on. And then your entire matrix would be AN. Okay. So those are the leading principal submatrices. And then you have the principal minors. Which I'll call U sub K. Those are just the determinants of the leading principal submatrices.
So AN would be the whole matrix.
Right. Yeah.
Okay. So like A1 is included in A2. And
Yeah,
A1
it's like those
is
Russian
included.
dolls. Yeah.
Right. Okay.
Okay. Now I'm gonna refresh your well, actually, let's see if anybody remembers. Where did I bring these up before?
Previous session, I think. I
Um,
mean, a few sessions ago, I've seen
Oh,
that.
I read it today.
okay.
It's right here.
Okay.
Yeah. Okay. These were used before for what purpose?
LU.
Yeah. What about LU?
I mean, I can flip my notes. Stephanie's flipping her notes.
Okay.
Oh, no, we're gonna read it.
Well, I bet someone's scrolling for notes too.
I know it was an LU.
Yeah.
I can flip and find it. That's not as much
Yeah,
fun though.
Okay. So this is why I would not expect you to remember something from 5 years ago.
Right. Struggling last class.
Well,
I
it wasn't
had
last class, but
something about the determinant.
Oh, to make sure that LU exists.
yeah, this is So, so for general A, we can say that A equals LU exists if and only if all the principal minors are non-zero. So that means you never have to pivot. I mean, it might be a good idea to, but you're not required to. But what we care about today is if A is symmetric, then we can say that A is also positive definite if and only if all of the principal minors are strictly positive. And this has to be true for all K from 1 to N. So in the class we took 5 years ago, early in the semester, you guys carried that out. Like you're finding the minimum of a function of multiple variables, and you compute your Hessian matrix of second partial derivatives, and you check if it's positive definite this way to see if it's a minimum or if it is positive definite, it was a minimum, and if it was negative definite, that means that's to all alternate in sign, starting with a negative, then it might be a maximum and so forth. Okay, and even for a small matrix like in that class, it's still pretty tedious. Yeah. Well, the thing is, because there are determinants involved, so this performing this check takes order n cubed floating point operations. So it's a real pain to check how matrices has an LU for general case, or if it's symmetric, check if it's positive definite. So in this case, instead of trying to check if LU exists, you might as well just try to compute it and see if it fails. And in fact, we're going to do something similar with positive definite matrices, because so what that means is, so if the matrix is positive definite, what does that mean? What's the consequence of that if you're going to solve a system with it using Gaussian elimination, based on what I've written on this board? Or what is nice about symmetric positive definite matrices when it comes to Gaussian elimination?
Costly.
We'll come to that later. But
But it says,
okay, go ahead.
I don't know, they won't fail, right?
Define not fail.
I remember you talking about like having a 0 as one of the entries and not dividing by.
Well, yeah, because and again, when that happens, what are you supposed to do to get around it?
Or
Pivoting?
Pivoting. Yeah. All right. So, so based on what I've written here, if matrix is positive definite, then it has what factorization? It has an LU factorization.
Yeah.
Because if its principal minors should be positive, and of course they're non-zero,
Right.
so we never have to pivot. So, yes, it would be a little cheaper because you don't have to do the comparisons necessary. Now, like I said, it may still be a good idea just to reduce the size of your multipliers, but you would never have a situation where you end up falling into this trap of having to divide by 0 just to do the row operations.
So if it's symmetric positive definite, you can still break it into the LU factorization. You just don't have to pivot to do that.
Right.
Is that what you're saying?
You know that you'll never have that 0 diagonal entry creep up anywhere in the process.
Okay.
Because if you have a general matrix, you don't know anything about it. You might say, okay, your 1, 1 entry is fine, it's not 0. you don't know that there's some surprise zero diagonal entry waiting to jump out and get you further down the matrix. You can't tell by looking.
All the diagonal entries are greater than 0.
At the start, yes,
Oh,
but
once you thought you're.
yeah, because you do these row operations that change them. Yeah, so you can't tell. But if you know for any reason that the matrix is positive definite, you know it's never going to happen.
So excuse me, what you said that during the operation, it is okay if diagonals become 0.
No, but they're not going to. That's the point.
Okay, even during the operation.
Right. Yeah, but it'll never happen because of this. Yeah, so that's something you can count on if you know it's positive definite. If you don't know it's positive definite, then you're going to spend a lot of effort checking. So you might as well try to do LU. But in fact, we're not going to do LU either. So actually, the point about LU and positive definite matrices is pointless because we're not going to do it anyway. And the reason why is we can do it more. We can solve systems involving positive definite matrices more cheaply than to do this Gaussian elimination even without pivoting.
More cheaply.
What?
More cheaply.
Yes.
Okay.
Okay. All right. And for that, we can use, so it's instead of Gaussian elimination, but to solve AX equals B, in the case where A is, and I'm going to use an abbreviation because it's very commonly used in the community, SPD, so symmetric positive definite. Because I'm going to get tired of writing symmetric positive definite all the time. So in this case, we use what is called the Cholesky factorization. Now, Cholesky factorization is written in different ways, but the way I'm going to write it is A is equal to G transpose, where G is a lower triangular matrix, and each diagonal entry of G is strictly positive. That requirement is put in to ensure uniqueness, because if you allow G to have negative diagonal entries, and you could, but then it wouldn't be unique anymore. But we'd like to have uniqueness. So you can think of this as really kind of like a slight variation on LU, because LU is a factorization of A into a lower triangular times an upper triangular. And that's what we have too. Lower triangular times its own transpose, which is upper triangular. This is not unit anymore, because we like to have the symmetry between them. Okay. So what I need to do is derive the algorithm for the Cholesky factorization. But just because I have it written here, and to justify all the work to do that, the cost of computing this factorization is is 1/3 n cubed plus. All right, so you can solve a system involving the symmetric positive definite matrix in about half the operations as for a general matrix, and it's because of the symmetry of the factors involved. Okay, so that's what we use for Cholesky. And I remember whenever I teach this class before, or even when I bring up this kind of matrix in a different class like 561, that it's very important that you associate Cholesky factorization with symmetric positive definite matrices. And what I mean by that is, if you have a problem come up, like a homework problem, involving a symmetric positive definite matrix, it's often very helpful to use the fact that it has a Cholesky factorization. So, in fact, this is another characterization of positive definiteness, that A has a Cholesky factorization if and only if it is symmetric positive definite. In fact, an effective way to check if A is symmetric positive definite is to go ahead and try to compute Cholesky. And if it's not, it'll fail. Because what you're going to see is Cholesky factorization involves square roots. And if you end up either computing a square root of a negative number or dividing by 0, then it fails. And in that case, you know the matrix is not symmetric positive definite. Because doing this is actually cheaper. Well, yeah, I guess it would be cheaper than just trying to compute all those dang determinants. So you might as well just do that. Because then if it works, then you have factorization and you can solve a system.
I don't understand how people got that coefficient of flops for Cholesky factorization.
Oh, yeah, it's not something you would necessarily be able to like read off the algorithm, but it really comes from the fact that you're computing one set of entries of a triangular matrix instead of two, because you're having to, like in LU, you're computing these multipliers, and you're also computing these entries of U. So twice as many entities. So the fact that you can reuse the same data for different purposes helps cut down that cost. So the idea, so I'm harping on this now so that when you have a problem where you're assuming a matrix is symmetric positive definite, it should be an automatic trigger. Oh, it has a Cholesky factorization. Maybe I can use that to make a problem easier. Hint, hint. So, and apparently I've done a good enough job of hammering that point home because I once had a student who actually probably all of you know, who wrote in their student evaluation at the end of a semester, wrote only this comment. When I think symmetric positive definite systems, I think Cholesky.
I'm sure you can always tell if you write what. Sure.
Especially in smaller classes, yeah.
We should all say funny stuff on purpose.
Yes, but all of you do might have a hard time.
That's true.
Well, it'd certainly be better than some of the crazy things I get, especially from undergrads. Okay. Now, how are we going to come up with this algorithm? Whoops, wrong page. For the factorization. So I'm going to recall a property of matrix multiplication in general that's going to help us here. So we have a general matrix product, C is equal to AB. And A has this column partition, and we'll assume that everything is n by n. And then B has a row partition, then we can actually express a product as a sum of outer products of each column of A, outer product of each row, of a corresponding row of B. So we have that. So if I apply this to a symmetric positive definite matrix A, then we have this Cholesky factorization, and I can express G, that's still unknown at this point, using a column partition, and I can say that A is equal to this sum of each column of G, outer product, each row of G transpose, but that's going to be a transpose of that same column, plus you. So I can write it this way. All take a individual entry of that. So, so AIK, and to take an entry of A, the IK entry, that's the same as multiplying on the left by EI, and multiplying on the right by EK. So now I can do the same thing in the sum. So I have EI transpose GJ, that's a dot product, and then I have GJ transpose EK, also a dot product. But all I'm doing here is like I'm extracting the ith element of this column, and here I'm extracting the kth element of this row. So that would be a sum. Okay. So this is going to be Gij, and then what I have here is going to be, well, this is the kth element of the jth column again. So it's going to be GKJ. All right. But now there's something more I can do, because I have to take into account the fact that G is lower triangular. So what that means is, so here we have this entry, GKJ. Well, the only way that entry is, that J is going from 1 to n. But because G is lower triangular, so this right here equals 0 if the row is strictly less than the column. So K is strictly less than J. So there's no point in including the terms in this sum where J is greater than K. They're going to be 0 anyway. So I can cross that out. I can say J equals 1 to K. So in other words, I'm forcing a condition that J is now less than or equal to K. So any questions about, oh, dang it. Okay, whoever's watching this is really going to be pissed at me by now. Sorry to whoever's watching at home. Okay, so that's what happened. Okay. So any questions about how that sum came about? This is going to be my key to obtaining the algorithm for Cholesky. All right. Because the idea is I'm going to compute G one column at a time. So starting from a first column and then advancing after that. Okay. So what I can do is I can do this like in a sort of like in a inductive manner. So suppose I've already computed computed G1, G2, up to Gj gj minus 1. So we have that part of g. How do we compute gj? Well, first, I'd like to get those previously computed columns completely out of the picture. So the first thing I do is I'm going to, because I have an expansion of A in terms of these outer products of columns of G with itself. So I'm going to subtract off those outer products for columns I already have. All right, so I'm just going to take them out of A completely. Okay. Then, I'm going to return to this sum that I have here that lets me express entries of A in terms of entries of G. But now I can trim it down because I've just taken out everything that involves a column of G less than J and taken it out of the matrix. So actually, no, I need to change my notation here. Hold on. Yeah. I need to switch roles of J and K here. Okay. From what I had in the previous board. Okay. I need to match my pseudocode that's coming later. Okay, so now anything that has a column of G less than J, it's already been subtracted off. So this summation goes away, except for the last term. So it's going to be G I J G J J. Because of the subtraction I've done before. Okay. So, now keep in mind, G is lower triangular. So I only care about the case where the row is greater than or equal to the column. I is greater than or equal to J. All right. So right now I don't know anything about column J, but I'm about to figure it out. So the first thing I'll do is I'll set, since I only care about the case where I is greater than or equal to J, I'll start with I equal to J. So let's see what happens in this equation in this case. Now I have AJJ over here. And then over here I have GJJ squared. Well, now I can just solve for GJJ. This is square root of AJJ after I subtracted all those things off from step 1. And now I can go back here for a case where I is strictly greater than J. So for I is equal to J plus 1, J plus 2, etc., all the way up to N, what is Gij? Yeah, but for I greater than j.
Aij over square ajj.
Yes.
JJ.
Yeah.
Yeah.
So aij, and yeah, it's a square root, but now we know what that is. It's this.
It's
Yeah.
Right.
GJJ. Okay. So now, column J of G. I'm this close to a tongue twister here. Column J of G is now complete. We now know what it is. But then what we might as well do, now that we have that column, we can go back up here and subtract it off from A to set up a computation of the next column. Okay. So now we can put these pieces together to actually have an algorithm for the full Cholesky decomposition. So, what does this entail? We compute the columns one at a time, like I've been describing. Okay. So the idea in filling in the contents of this loop is, I'm going to assume that at this point, right here, whatever outer products I needed to subtract off, I've already done so. So I can start right here, take the square root. So I'll make a comment in this code. Well, I'll use a MATLAB %sign. Because I just know you guys are waiting to type this code in MATLAB, aren't you? So compute column J of G. So we go ahead with the square root. And then we compute the rest of that column, and that's going to include another loop, the one I have down there. So I equals j plus 1, j plus 2, up to n. And we'll perform that division that I have there. And that fills out the rest of column J. And here is where we set up the next iteration by subtracting off that outer product involving column J. And that's going to require another loop. So if we look back here, well, let's see. It's column J I need to deal with. So, okay. Well, actually, the other way that I wrote the sum earlier is what's going to help me here. So I have this sum of outer products, and the term corresponding to column J, that's what I want to subtract off. So my loop is going to run from, well, I already have a loop over I. And now I also need a loop over K. And that's going to go from J plus 1, J plus 2, up to I, where I'm going to update AIK, because in order to compute G, which is lower triangular, and so the way I've written this loop, what that means is I is greater than or equal to K. I'm only dealing with the lower triangle of A. I don't have to do anything to the other triangle. And it's symmetric anyway. So I have AIK, and then I'm going to subtract off that, which only involves entries from column J of G, which I've just computed. So G, I, J, G, K, J. And that's it. That computes the Cholesky factorization. So what's happening in here well, really, it needs both these loops. A is having subtracted from it GJ transpose, but this subtraction is only happening in the lower triangle. And that is a key reason why, because this is the most expensive part of Cholesky factorization right here, because it's happening within 3 levels of loops. But because it's only being done in the lower triangle, that's why Cholesky factorization costs half as much as LU decomposition. Because so what's happening is in LU factorization, the whole matrix gets touched, essentially, but not here. Only half of it gets messed with. Okay. So because we subtracted off this outer product here, when we get to the next iteration, we know that A has had all previous outer products, like previously computed columns of G, taken out. And that's why we can go ahead and do this square root of these divisions. Oh, that should be G. No. Yes, that is G. GJJ in the division. Okay. Other questions about the algorithm? Yeah. So now I can just be coded up in MATLAB to go and do that. But that's not necessary, because in MATLAB there is a command for this. Although it behaves a little bit differently. Do R is equal to chol of A, then the factorization is R transpose R. So in other words, R is actually upper triangular. So it's like it doesn't give you the G, it gives you the G transpose. So you have to be careful about that. So different books write the Cholesky factorization in different ways, but it's always a lower triangular times an upper triangular. They differ in where they put the transpose to express that. So it's very similar to LU decomposition in that sense. Okay.
So if you want it to be lower triangular and use that command, then at the end we have to transpose it.
Yeah. If you do that, if you take what the output of that and transpose it, that's G. Okay. So just for fun, I'm going to show you what happens if I were to run this algorithm on a very small matrix that is not symmetric positive definite.
If I use help for chol, it will say that it is upper triangular.
Yeah, it explains it's what it returns. Okay, so as an example, let's suppose that A is equal to 4, 3, 3, 2. Now, there's nothing here that rules out, at least by a visual inspection, symmetric positive definite. I mean, it's symmetric. The largest element's in the diagonal. All the diagonal entries are positive, so there's no immediate warning signs. But let's see what happens if I run this algorithm. So for a case where j is equal to 1, I'm going to say that g11 is equal to the square root of a11. That's 2, so there's no problem. And then for I, it's going to run from j plus 1 up to n. So I is going to be equal to 2. So we're going to have Gij, so that's going to be 2,1 is equal to A21 divided by G11, so that's going to be 3 halves. Okay, so far so good. And then I have a number loop. K goes from j plus 1, so that k runs from 2 up to 2. So when k is equal to 2, I have a ik, so a22 is equal to itself, minus gij, so that's g21, times gkj, so that's g22. So that's going to be, a22 is 2 minus g21, which is 3 halves, times, oh wait, that's
What
right.
would be G21 again?
Yeah, g21. Yes, g21 squared. So 2 minus 9/4, so minus 1/4. And that already spells trouble. So then you go to j equal 2, and you get g22 is equal to the square root of the updated a22, which is 1/2 I. So that's unfortunate. So this matrix is not symmetric, positive, definite. Now, even though there were no obvious warning signs just by looking at the matrix, what is a warning sign that tells us not symmetric, positive, definite that would not be hard to see in this 2x2 case? Because I bet you certain properties, like largest element in the diagonal, positive diagonal entries, but there's another property that in this 2x2 case would not be hard to check. That must be true for symmetric, positive, definite.
One of them determined it had to be.
Yeah, determinant. So that was a determinant. Yeah, so 8 minus 9, so it's minus 1. So, which means that the eigenvalues are different signs. So we wouldn't have all positive eigenvalues. Okay, so sometimes I've had it happen where I feed some matrix into MATLAB's control command, and it comes back and says, well, this matrix is not positive definite. So what happened was it tried to run its algorithm, and either it ended up taking the square root of a negative number, or the quantity we're taking the square root of might be 0, and that's okay here, but what happens for an algebra? It has to divide by it.
Yeah.
So, actually, I should mention a related class of matrices. A matrix is symmetric, positive, semi-definite. Means that, well, symmetric and x transpose AX is greater than or equal to 0. So for instance, if it has a 0 eigenvalue, that can happen. So symmetric, positive, semi-definite matrices are also of interest in certain applications. So what would happen in that case, but that still is not going to have a Cholesky factorization. So it has to be strictly symmetric, positive, definite for that. Okay. All right, how much time do I have? Oh, not much, but it'll be enough. All right, well, enough to finish Cholesky. There's another class of matrices I want to talk about, banded matrices, so that will come up on Thursday. That's not relevant to the second homework anyway. Okay. So, to solve AX equals B, if A is SPD, so first you compute the Cholesky factorization. A equals GG transpose, and that takes 1/3 n cubed floating point operations. And then the rest of the process is very similar to what you would do with a general matrix when you're doing Gaussian elimination substitution. So you solve gy is equal to b. So that's using forward substitution. So that takes order n squared flops. I should mention that sometimes some books you see Cholesky spelled with an I instead of a Y. Also, a little trivia for you. So my advisor, Gene Golub, the computer he had in his office, the host name was cholesky.stanford.edu. Okay, and then once that's taken care of, then you do back substitution with G transpose. Which is n squared plus. Now, when I described forward substitution before when I wrote out the algorithm, I was not dividing by a diagonal entry in that case because in that situation L was unit lower triangular. Diagonal entries are 1, there was no need. But here you do have to divide by a diagonal entry of G in both forward and back substitution. And the last point I want to make is actually about a closely related factorization. Actually, it's related to both Cholesky and to LU. So for general A, well, I guess not entirely general, if it has an LU factorization. So you can write A is equal to LU, but then what I can do is I can separate U into two matrices, where a diagonal matrix times a matrix M transpose that is unit upper triangular. So L is unit lower triangular. It's the exact same L as in the LU factorization. D is a diagonal matrix, and M transpose is unit upper triangular. So in fact, you could say that Uij is equal to Djj Mji. And I have Mji because it's M transpose up there. So that's how the two are related. Now, so this is the LDMT factorization. That itself isn't really of interest until you have, also we need the diagonal entries of D to at least be non-zero for this to be practical. Well, actually, that would be true from A being invertible. So things get more interesting in the case where A is symmetric. So what happens in that case? Okay. Let's see. You have A equals A transpose, so that means that LDM transpose is equal to the transpose of this, which is equal to MD again, because D is diagonal, so it's equal to its own transpose. L transpose. And now L and M are unit triangular matrices, lower or upper, so they're invertible. So I can multiply both sides on the left by M inverse. And I can also multiply both sides on the right by L inverse. Let's see. How do I want to do this? Okay. Yeah. Or actually, yeah. No, I want to multiply on the right by M inverse transpose. But that's going to give you this M inverse L, the whole thing transpose. Now, M and L are both unit lower triangular. So both of these matrices in here, so this is unit lower triangular. This inside the transpose is unit lower triangular. But now, and the thing is, D is diagonal, which doesn't affect triangularity. But now I'm transposing this. So this whole side is lower triangular. This whole side is upper triangular. So what's true of both sides?
It's gotta be the identity, right? Or diagonal.
Diagonal. If both sides are diagonal. But D is already known to be diagonal. So that means that M inverse L is diagonal. But the diagonal entries of M and L are both 1. So what that means is M inverse L is identity. So in other words, M equals L. So in this case, A has what's called an LDLT factorization. So it's LDL transpose. So it makes sense if A is symmetric, then it should have some sort of factorization that is symmetric. So now let's take it one step further. A is SPD. We have this LDLT factorization, but now I'm going to break up the D into D to the 1/2 times D to the 1/2. So that's the same as LD to the 1/2, and then D is diagonal, so it's equal to its own transpose. And then we have LD to the 1/2 transpose. Now, what kind of matrix structure-wise is L times D to the 1/2?
Unit lower triangular.
What?
Unit lower triangle.
L is unit lower triangular. D is any diagonal matrix. Yeah, just plain lower triangular, no unit. But if A is equal to a lower triangular matrix times its own transpose, this is, what is this? So LD to the 1/2 is also known as G. That is the Cholesky factor. Okay. So what's interesting is, okay, so if A is symmetric plus definite, you could compute Cholesky factorization and do all that. Or you can compute the LDLT factorization and use that instead. So this, for this reason, and I didn't cover this, it's in the notes. The algorithm is given there. It doesn't involve any square roots. And square root, in terms of floating point arithmetic, is actually a more expensive operation than the addition, subtraction, multiplication, division. So this is actually called square root free Cholesky. So some people like to use that. Now, if A is symmetric but not positive definite, LDLT can still exist. So you might have a case where D is a diagonal matrix that does not have all positive entries. Some could be negative. If it's any or 0, then you're in trouble because it's symmetric. It's not symmetric, it's singular. So you wouldn't be able to solve a system that way. Actually, looking at the algorithm for LDLT, where did I put it? Oh, here it is. There are divisions involved. In the LDLT algorithm, you're dividing by DJJ. So if any of those entries are 0, it's over. But you can have a matrix that, for instance, is indefinite. It has a mix of positive and negative eigenvalues, for example. So in that case, you'd have LDLT with positive and negative entries of D, and that's perfectly okay. So in that sense, LDLT is more flexible than Cholesky, because it could apply to symmetric indefinite matrices. Also, you get the same cost savings as with Cholesky because of asymmetry. You have the same matrix on the left and right. So this takes 1/3 n cubed floating point operations. So that's it for symmetric and especially positive definite matrices, and then I'll cover banded matrices on Thursday. But now you can finish homework 2.